genotype. We don't know. They could be big P, or they could be big P, little p. You look at the person, you ask whether they can metabolize phenylalanine, you ask if they have good enzyme. They do. We just don't know unless we do a genetic test. All right, so now we're going to cross them like this. We're going to cross two carriers. So what happened? How are this woman born, these two sisters born that I showed you? They both had normal parents. They both had normal parents. The parents married, they had kids. Both their children have the disease. So both parents must be, they absolutely must be big P, little p. Otherwise they couldn't have children who have little p, which is what they have. So they get together and they mate, and here's what happens. So we do what's called a Punnett square. So the mother is going to contribute gametes that are either like this or they're like this. One or the other, right? You only have one chromosome that you're following. Half your gametes are going to be big P, half are going to be little p. The father does the same thing. So we put them together in all combinations, and that's what you get. That's what's called a Punnett square. It's the simplest way to predict what's going to happen. So 1/4 of the children should be big P, big P. They will look normal. They will be normal. And they will not be carriers, right? 1/2 the children will look normal, and they will be carriers. 1/4 of the children will be little p, they'll have phenotype. All right? Now, this is probability, this is not certainty. So you say, well, they had two children, both of them had PKU, how could that happen? Well, if they had 20,000 children, I would predict that 1/4 of them would be little p, but they would be tired, believe me. Taking care of all those kids would be a big problem. So, if we look at this, then we say, determine the ratio of probability. The genotypic ratio is there's 1 PP to 2 big P to 2 big P little p's to 1 little p. That's the genotypic ratio. And the phenotypic ratio is 3 to 1, right? Because all three of these boxes are the same phenotype. They're different genotypes. True. Same phenotype. Normal or PKU. The normals are here. The PKU is here. Right? So now you know the rules of probability, and so you can assign numbers. You say 1/4 this, 1/2 this, 1/4 that. So if you have two carriers and they mate, then the probability of them producing carriers is 1/2. The probability of producing a child with little p is 1/4. So this is where gambling comes in, right? If you had a 4-sided coin, I know it's a little hard to imagine, and only one side paid off in gambling, right? There are 4 different colors on it. You throw it up, and only one color gets paid, right? That means a probability of 1/4 of you getting paid, right? Yeah, on occasion. You'll get 2 of them in a row, right? That's like having 2 PKU kids in a row if both parents are carriers. But, on average, that's a bad bet, unless you're getting a good return. Certainly for 1-to-1, it's a terrible bet. Let's say you bet $1 and you get $2 if you win. That's a bad bet. That's a really bad bet. Because 3/4 of the time you're going to lose and only 1/4 of the time you're going to win. And you're only going to get paid $2 for a win. It's a bad, bad bet. So just don't do it. You know, the games that attract the most attention of the big gamblers in Las Vegas and places like that are ones where the probability of winning or losing is about 50-50. Then it actually makes sense to gamble if you know what you're doing. All right, you ever read James Bond? See Casino Royale? It depends on Baccarat. That's a game of 50-50 probability, essentially. So you're going to have 3/4 normal, 1/4 PKU. That's the idea. So, two-thirds of the individuals who are normal will be carriers. Does everyone see that? See how I'm reasoning from my data? If I take, let's say these people had 30 kids. If I take all the normals from them, 2/3 of them will be carriers. Does that make sense to you? I know they're normal, so they have to be in this group, right? And this tells us that 2 out of 3 will be carriers, right? That's how you reason from your data. So these are where all these numbers come from. So this is the kind of thing we're trying to get you to do. Okay, so here are my 3 children. We talked about their eye color, but the fact is that they're nerds. You know? The nerd phenotype is determined by the nerd gene. I hate to tell you this, and it's dominant. The big N is dominant over little n. Ron and Christine are nerds. We're both nerds. My wife is an English professor. I'm a biology professor. You know we're both nerds. And have 3 nerd children. All 3 of our children are nerds. And what I want to know are what are my genotype and my wife's genotypes. What are they? Can you tell me from my children? I'm a nerd. My wife's a nerd. All 3 of my children are a nerd. What's my genotype? What?
You can't tell.
You can't tell. You can't tell. You absolutely cannot tell which is the case. Here, let's say that I'm big N, little n. And let's say my wife is big N, little n. All right? Let's do the Punnett here, right? What are we going to get? We're going to get then we're going to get. So the probability is that only 1/4 of my children will be not nerds, right? So, whereas 3/4 of my children, each time we have a meeting, there's a 3/4 probability that they'll be a nerd, right? So I have 3 children, so it's 3/4 times 3/4 times 3/4 that they'll all be nerds. And that's not so bad. It's 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. So it's 27/64ths that all 3 of them will be nerds. So the only way to really tell is for me to have a lot of children, see if a non-nerd pops up. Every once in a while, you have to do a lot of crosses, but Christine didn't want to do that to figure it out. But there's a simpler way, and she was even less likely to consent to this, which is, how can we find out? You can find out by taking me and test crossing me to a non-nerd. But she didn't want that. I have no idea why. I tried to convince her, but I said, we've got to determine whether I'm heterozygous or homozygous. I said, we can do the same for you. So you have to mate me to someone who is not a nerd. We know that person is little n. We don't know what I am, but if I mate to them, I'll know right away whether, pretty much, after a few kids anyway, whether my genotype is big N, big N. If I'm big N, and I mate to this person, all my children will be nerds. Every one of them. Every single one. Right? Because they're all going to get a big N from me. No matter what they get from their mother, it doesn't matter. Because I will determine their phenotype. Not their genotype, but their phenotype. But if I'm big N, little n, then I expect half the children from that mating to be normal. Let's do it. If I'm big N, and I mate with a non-nerd, then half the children will be big N, little n, and half the children will be little n, little n. So that's how we could determine it. But again, it just didn't happen. So, but we can do this with genetic organisms. And Mendel did it with peas. He liked peas. He worked with peas. You can do it with fruit flies. So here we go. We have a gene, little r, that causes wrinkled seeds. The big R version of it is a round pea, and big R is dominant over little r. So if we test cross an unknown round seed with a wrinkled seed, which must be homozygous recessive, then all the peas will be round. That proves that this pea was homozygous. Here's another gene. It's the yellow gene. Yellow is dominant over green in peas. You didn't know that, did you? Isn't that weird? Yellow is the dominant color of peas in peas. So, but let's say we have a yellow individual. We don't know whether it's big Y, or big Y, little y. But we cross it and we find that half of the peas that are produced are this and half are this. That proves that that guy was a heterozygote, right? Does everyone agree with that? All right. So now you're learning laws of probability. So this is just saying what I said.